All right. So far we've looked at the mean value geometrically, the mean value theorem geometrically. It says that if a function is continuous on the closed interval and differentiable on the open, there's going to be at least one place in that open interval such that the slope of the tangent line is equal to the slope of the secant line. In other words, that those lines are parallel. Now let's look at this formula contextually and then do an example of the mean value theorem, a real world example. Okay? So contextually, f prime of c is the instantaneous rate of change. Of what function? F of x, where at x equals that number c. Whereas this is my average rate of change. Of what function? Of f over what interval in the domain? A to B. So what we're saying in context, if a function is differentiable and continuous on that closed and open intervals respectively, then there's got to be a c, there's got to be a moment in that open interval such that the instantaneous rate of change is equal to the average rate of change. That's what this formula is saying right here. The instantaneous is equal to the average over or on AB. All right, and that should make sense. For an example, if you are driving to school and you have an average speed, or more accurately, an average velocity of, say, 30 miles per hour, doing a lot of freeway driving, then there must be at least one moment in time. Oh, I wrote a 3 instead of a C. How silly. There's got to be at least one moment in time while you're driving when you actually go 30 miles an hour. In fact, there's going to be lots of moments with that particular example, moments in time, where you're going to be doing your average speed, your average velocity. So with that said, we're going to do a similar type situation utilizing the mean value theorem here in example 3. All right, so a pebble is dropped from an initial height of 784 feet. The height of the pebble at time t seconds is given by this position function. H of t is minus 16t squared plus 784. We're asked to find the time t guaranteed by the mean value theorem when that instantaneous velocity is equal to the average velocity during the pebble's trajectory. So we have a picture, say like this. Here we are up at 700, it's not going to be to scale, 784 feet. That's at time 0. And the pebble is being dropped, and then it hits the ground. Yeah? That's the whole trajectory. Now we know that this function, that parabola, looks more like this, but there's only a portion of the parabola that makes sense to model this situation, right? We don't have negative time, and the parabola can't the pebble isn't falling through the earth. So the first thing that we need to do is we need to figure out when the pebble hits the ground, so then we know the length of the trajectory. We know what average rate of change to calculate over what time interval. Right? So to calculate the average velocity, change in position over change in time, over the trajectory, we need to first know when, for what t value, the pebble hits the ground. Well, when the pebble hits the ground, the height is 0, right? So I'm going to take my height function and set it equal to 0 and solve for t, solve for the moment in time when the height is 0. Let's go ahead and factor out that minus 16, the GCF here. Can divide both sides by minus 16 if you want. We have t minus 7 and t plus 7 is equal to 0. So my t values that make my h value 0 are t equals 7 or t equals minus 7. And it doesn't make sense to have negative time, right? This part of the model doesn't make sense. Here we are at t equals 7. Right, so here is, that's an equal sign up there. Time 0, the pebble is up at 784 feet. You can label feet and seconds if we want. Then 7 seconds later, we've hit the ground. So now I'm ready to go ahead and calculate my average velocity over this trajectory, which is the slope of this secant line. Okay? Average velocity, slope of secant, is equal to f of 7, let's get the picture on there, minus f of 0 all over 7 minus 0. Okay. And your OCD teacher didn't change any math, but I just changed these colors because I was thinking back, this matters for some of us. I was doing orange for B and blue for A, and so I decided to just go ahead and keep those the same. All right, duplicate. So f of 7, just plug, oh, and I'm using f, and what's the name of this function? It's named h. Okay. H. All right, so I have this written down here to save myself some scrolling. H of 7 will be minus 16 times 7 squared plus 784. minus h of 0. H of 0 we know to be 784, all over 7 minus 0, which is 7. And this ends up being minus 112. And you can calculate that on your calculator. 784s are going to cancel. We've got 7 times 7 times a minus 16 in the numerator divided by 7. We just have minus 16 times 7. Okay, so here is my average rate of change. Now we need to take a derivative, and then we'll set the derivative equal to minus 112 and find the t-value such that that instantaneous rate of change is equal to this average rate of change. So here's my function, minus 16t squared plus 784. My velocity is the rate at which position changes with respect to time. In this case, I'm using h for the position of the pebble being the height that it is off the ground. Minus 16 times 2 is minus 32t, plus the derivative of a constant is 0, so plus 0. And we're going to set these two equal to each other. And we want to solve for the t that makes this true. Dividing both sides by minus 32, we get t is equal to 3.5 seconds. So if we go back to this picture, let's put this on the next page. My average velocity, the slope of my secant line, is minus 112 feet per second, right? My average velocity is minus 112 feet per second. The instantaneous velocity at 3.5 seconds is the slope of this tangent line. The instantaneous at t equals 3.5 seconds is also minus 112 feet per second. It's equal to that average velocity. The negative velocity just means that my pebble is on its way down, so it's traveling at a speed of 112 feet per second, and it's on its way down. Okay, and we are done. We were asked to solve for the t guaranteed by the mean value theorem. Here is the t. Done. Okay, let's look at it on Desmos just for fun, and that'll conclude this video. Okay. So here is my position function, my height function in black, the path of my pebble, the height that it is off the ground. And we see that my average velocity is minus 112 feet per second. Moving my slider here, all the slopes of those tangent lines are instantaneous velocities. Right, let's see it turn green. Ah, it's so satisfying. At t equals 3.5 seconds, my instantaneous velocity and my average velocity are the same. In this case, they're both minus 112 feet per second. We're traveling at a speed of 112 feet per second, and we are on our way down. Next, in this think, pair, share, I want you to go ahead and try to do that on your own. I'm not going to make a video of it because it's exactly like the work that we just did, but I will post the filled out lecture notes of it.